Vamos então arrancar já para o primeiro speaker desta manhã, o primeiro internacional de hoje. Portanto, please welcome on stage our first speaker, Wolfgang Merkt.
Good morning. How are you doing? Great. I'm really excited to be here today. It's great to be back in Porto, and I'm going to tell you a little bit about the work that we've been doing in robotics, why it's a really interesting field, and I think why it's something that, as a computer scientist, it's something that it might be interesting for you to get into later. So, for people, it has been an incredibly interesting area of application, and kind of like an endeavor that they've been pursuing for hundreds of centuries to make things move like we do. So this is a very early machine. This is kind of from the clockwork age. It's 240 years old, and just based on very intricate mechanical design, it's able to write the name and the address of its creator. But what I think is really exciting is that at the moment we're living in really exciting times. The convergence of a lot of exponential technologies, that is those that are doubling in their price performance year over year, and Moore's law that you might be very familiar with is just one example of those. And all of these extending are helping robotics to really, really break out as we speak. The sensors are becoming more and more powerful year over year. We have more and more computation to translate what we're sensing into action, and we're having better manufacturing to miniaturizing components for robotics and then being able to execute. So what we may not know now is that robotics has been an increasing part of our life for the last few years. It has been breaking in the background into our lives, fulfilling our orders with over 100,000 robots now shipping and preparing your orders at Amazon. It has been creating and mining all the ore that goes into the Coca-Cola and Red Bull cans that you may be drinking, and it's at the backbone of a lot of the advances that are driving the comfort of society today. But now we're really at this time where robotics is breaking into the daily lives, where it's touching us through the media coverage as well as through what you may be seeing coming over the next few years, preparing your coffee, delivering your pizza, flipping burgers, and really being more present in our lives. However, moving robots into our daily lives and delivering consumer products is incredibly hard. And unintended stuff just happens, like shit literally happens, because you can't always encode all the knowledge, all the corner cases, everything that you may want to target, even for very simple products such as a robotic cleaner. Perception may still be something that can't be fully thought through at the beginning, and in this time that we're having robots enter our life, we may actually get into a time where stuff happens that is not quite as intended. And on the other hand, things that you may have seen in recent years is that research robotics is making huge strides and incredible performances that are hard to believe. So this robot, you've probably seen it, is 1.5 meters tall, close to 100 kilograms, and it can move as dynamic or even more dynamic as a human can. But what roboticists that actually work in the field are more familiar with is something like this, where it's very, very common for robots to fail and fall. It may be fairly frustrating if you're working in the field to see that, but that is more what we're used to. So the big question is what is really the implication of practical robotics, and what does it mean, or what is holding us back from achieving more? And quite frankly, to be honest, you may have seen it, but the category of these failures is pretty much twofold. Half of what you see here is because people made mistakes, and only a little bit is because the robots couldn't quite do it. All right, enough falling robots. So what I'm going to focus on today is three things. First, why is robotics actually hard, and why don't we see more robots sooner near us or caring for us? And that kind of focuses on what are like the challenges you may face and what we're doing in research. The second is, why do we even want to talk about humanoids? So what is so inspiring and really drives us to work in it? And what do you have to consider when you want to build robots that go into space and work in space? And then how both of these first parts really fuel some of the research that we've been doing. And I will show you some examples and what that could mean for the future of industrial automation, especially back here in Europe when robots are becoming more and more pervasive in more walks of our life. As a little backdrop, I'm probably only slightly older than most of you here, but my journey has started very early in robotics. Like, I've been fascinated by making things move and seeing how things move. So when I was 14, I decided to partner up with the largest manufacturer of industrial robots and actually build something like an autonomous kitchen which does the food for you. Like, literally send it a text message. This was before the smartphones were around, and it kind of like gives you a call back once your food is ready or once you go home. So after that, I decided to study engineering. So I'm not quite a computer scientist by trade. I did mechanical engineering and management and did a lot of startups in between, and then went for different stations and internships in industrial and service robotics to do a thesis in like machine learning for transferring motions that you capture to very different morphologies. So when you have a look at this transfer here from the demonstrator to the robot, the arms are quite different shaped. And it's actually really difficult to figure out how you get a motion that somebody is doing in the room to be on a robot without the robot destructing itself and hitting its arms. From then on, I went to Silicon Valley, came back, did a master's, and currently I'm a PhD student. And since very recently, we're also working, based on what you'll be seeing today, on a startup. The next step is really, so why is robotics really that hard to translate if you want to execute a fairly simple task in a fairly simple environment in our daily environment? And what we can achieve in simulation is very impressive. So you have a lot of moving obstacles, you have robots in move, and you have to pick objects while everything in the scene is moving. And then with a lot of engineering and a lot of effort and a lot of people, you can translate that into impressive lab demonstrations that work on real sensing, that take input from the environment. So on the left top side, what you can see is the scene is fairly complicated for the robot because it has very limited ability to move, and it still has to be able to maneuver through this without colliding. And the challenge here is to really figure out how to do this really fast. And that is a very new way that we demonstrated how you could do that in 1 millisecond, which is kind of like a 1 or 2 order of magnitude step up from what you usually do. The second on the right-hand side was about how do you, through very remote, so you essentially sit in front of a laptop a couple buildings away, how do you control a robot in a different environment? So that's what you would do in a disaster scenario where you're very far from the robot. And then we have a lot of work recently on a humanoid that I'm going to show you later. Similarly, we can adapt to environments, and we can work really fast. So what you can see here on the left-hand side is a way how to do tracking of objects so that the robot can figure out how do I need to change. It's not all fixed as you may have it in an industrial environment. On the right-hand side, things are moving again, which is very challenging in the field of robotics where we prefer things to be fairly static. So I've just mentioned a few of the challenges, but there's actually loads if you want to move from what we see in labs to have it in the real world. And a few of the key things that we'll show through this presentation are especially perception, and how do you represent what you can perceive with sensors so that the algorithms that you build on top can actually make sense of it. And the key trade-off here is kind of like quality versus speed, and that most of the sensors that you can get, even when they're really expensive, are actually not that great or are just really, really slow. And that is kind of what's holding us back. And one of these examples is if you have a humanoid and you have a perfect knowledge of how things are going on in simulation and you want to run it on the robot, it may not work. And that's due to a multitude of issues. But a very visual one is you tell it to go somewhere, the thing in gold, and then it ends up somewhere entirely different just because of how it needs to keep balance, not fall over, or how there's a lot of issues that accumulate. And the other next issue is that even when the robot goes where you tell it to go, it may actually be different from where you intend it to be, because the sensing that you can get can have quite a large discrepancy from where it should be in the real world. So if you try to look at your hand and you're 2 centimeters off and you're trying to really get that bottle on the table, you may not just quite get it if you're just slightly off. So and what all of that translates to is kind of this example where again, this is all what the operator sees. So this is kind of like the user interface. You get all the sensing data streamed in, so that's live sensing from a stereo camera, and you can see the high quality LiDAR that gives you kind of like a feeling where you are in the building. And you're trying to pick up this box, and you just smash it in that case, I'd say. And it's not just in our labs where you can see it. You can literally see it all around. So if you first start with a simple perception failure, things are not quite where they seem to be. you get an unexpected contact, and yet another unexpected contact, and yet another, until you finally fail. And the challenge here for robots really is that as soon as you interact and as soon as you need to make contact, that's either you're walking or you're holding on to something, the whole dynamics of the system, the physics, they change, and it's very, very hard for a robot to figure out what to do. So it's not quite as reliable as we may want it to be. And if you want to go to space, this is the kind of requirement that the space agencies, NASA, ESA, whoever you talk to will put on you. You essentially need to get to reliability where you get 1 minute downtime in 500 days. Like, you don't want your oxygen system to ever fail, but you don't want your robots to fail either. So there's a lot of certification. You can't use the new and fancy algorithms, you can't pick up a library online, and you can't just use the latest computing equipment. Everything has to be certified. So you likely have to have CPUs that are about 10 to 15 years out of age. You may have to get every single library certified, and that can take a lot of time. So let's actually have a look at how this can look like. So the first question when we talk about humanoids that we always get is, why would you do legs? I mean, keeping balance is hard. You take a lot of energy to stand. You can just use tracks or wheels or any other way how to move. And the easy answer to that is, if we want a robot that operates in the environment that we do, the environment that was built for us, like buildings, streets, roads, stairs, there's a lot of things that we can't do if we don't have legs. And legs are actually pretty cool. So you can go over uneven terrain, you can go through very narrow gaps, and you can reach really high because you're fairly tall at a very, very slim form factor. So let's talk about Mars. If you want to go to Mars, it's actually quite far away. So everything you need to do years and years ahead. And everything you want to have, you need to essentially be able to ship. And that can actually take quite a long time. So there's no way for you to get spare parts up. So what are the mission requirements for robots in space? The first thing is we actually want to pre-deploy essentially everything. So think about the mission where you literally just drop cargo and habitats and all the supplies you will need for the entirety of your mission on the planet. And that's something that also prominently features in The Martian. And then because it takes so long to get the people up, which you want to launch like several years after you launch all the supporting equipment, you actually need to make sure that in this harsh environment on Mars, it still is in working condition when the humans come. And when you send them off and they're like on their way up there for half a year, you don't want something on Mars to break. So when they come, they kind of like are without oxygen. So the robots really have to be there and repair all the equipment. So they need to have ability to sense failure. They need to be able to like do surveillance, mapping, and compare it against what it should be. And then also very dexterous manipulation to fix all the habitats and all the essential equipment that we need on space. And then again, as you can't just send like spare parts for everything up, they need to be able to operate with equipment that was also built for people. So they need to be able to manufacture new components, and they need to be able to use the tools that the astronauts in that case would use. So let's have a look at a humanoid. That's a humanoid that we work with in Edinburgh in Scotland. It's one of 3 or 4 worldwide, and the only one that is outside of the United States. So this robot is about 1.82 meters tall. It's quite a bit taller than I am, and it weighs 140 kilograms. So that's quite a beast. Humanoids in general have a fairly high center of mass because most of our mass is in our torso, and for the robot it's actually the battery that carries most of the mass. And you may say it's bad because it's really hard to actually not fall over, but it's actually really good because the higher your center of mass is, the easier it is for you to actually keep balance by kind of like, it's similar to you taking a pen or a broom and balancing it on your finger. The next is robots that are not bolted to the ground are harder to control and harder to compute motion for, just because they move around in space, and you actually need to take care of all the dynamics that happen so they don't just topple over. And then you have a lot of motors for which you need to plan for. So it becomes a very complicated problem, and you need a lot of computing power to actually figure out what to do at any given time, and you need to do that at about 500 to 1,000 times a second. Yeah. So what's the sensing that you get on those robots? So there's kind of like 2 natures of visual sensing, and that's like live sensing data. So the first is a laser. A laser is a very slow but very high fidelity. So you get a really good field of view what is going on. And what you can literally see here with that high quality sensing, you can get a very accurate, with simple algorithms and open source libraries, a very accurate percept of the world. What is a table? What is an object? And you can almost just from these point data see what is actually going on. But it's very slow. It can take up to 30 seconds for you to get one of these images, so you can't just use it for reacting to changes in your environment. The second, and it's a faster sensor, is a stereo camera pair, and it gives you dense stereo, but as you can see from this, it's actually fairly hard to see what's going on, what the table is, if you don't have enough information, and it's very, very noisy. So most of your algorithms need a high level of robustness to deal with this. And all of these changes essentially mean that if you want to control one of these, a single one of these robots, you need a large team behind computers. And essentially for one robot, you may have 5, 6, 7 people monitoring every single change, approving every single thing that goes into it. And that may not be feasible if we're going to Mars. And the reason for that is we're having a large communication delay from you pushing the button for it to execute something to you seeing the result that can be 20 minutes, and you only get a very short window. So if we want to go to Mars, we need a new way of operating our robots. And that's very, very similar to what we want to see in the future of industrial automation. So if you look at a traditional factory where you may have encountered robots, we're looking at fast and very precise motion in an environment that we fully control. So what does that mean? The first thing is that we want to ensure is that we have repeatability. The task that the robot carries out now is the same that it will carry out in a few seconds, in a few minutes, in a few hours. The second is all of our robots are really rigidly attached to the ground, so you really know what's going on. There's not much variance. There's no dynamic effects from the environment, and we're protected and shielded from the human, from the people. So there's no risk, and you don't have to take that into account. And furthermore, we really have essentially unlimited power, which is not what you get on a robot, where you need to consider how do you really energy efficient get the most out of your battery. And then if we're looking at what's happening with the demographic change, with the rising labor cost, and the return of manufacturing to developed countries, what is often called reshoring, we kind of need a new way to do manufacturing, both here as well as in the Far East of Asia. And the big trend here is something that's called collaborative robots. So it's essentially a robot that is safe to operate without those fences. They can be directly next to you, and they can be flexible and agile and to be reprogrammed. But what you just saw here is the current generation of these isn't as safe as we'd like it to be. So they can still hit you and they can still injure you. So the motion that we're working towards is more one of a collaborative, where the robot senses what's going on, what you're doing, and first what you may want to do and adapt around it without having to stop. So it's a more efficient way of doing things. And the system that we propose to do that is a shared autonomy system. So the robot operates autonomously as long as it can. And when it senses that it can't, it stops and actually tells the operator what is going on and asks kind of for input. Or the operator, on the other hand, can take input at any given time and say, stop, I'll take over, I'll do a little, and then it goes back to full autonomy. So it allows a higher bit of efficiency just by allowing the best of both worlds to be adjoined. And at the heart of this is how we represent the environment for all the other algorithms, for figuring out how we do motion, for figuring out control, for figuring out whether someone is moving into the field of the robot. And so what we're doing here is we're actually using two things. The first is on the left-hand side, a really, really dense fusion of sensing. It's high fidelity. It goes up to like 1 millimeter, 2 millimeters accuracy. And it takes a little bit of time to compute, and that's very similar to what you get in virtual reality. So we're working very closely with people in that area. And from that, you then can figure out the semantic information, where objects are, how they roughly look like, and how you then would be able to interact with them, how you could grasp them, how you could pick them up. And the second is it looks a little bit more like Minecraft on the right-hand side. That's a way of representing the environment fairly quickly. And it's something where the robots can, in like 10, 20, 30 times a second, figure out, do I need to change, is something changing? And the whole process is kind of illustrated here. So you get several very dense sensors, so that's in this case a Kinect, and technology-wise. And that's a lot of data to process. So you need 2 to 3 computers to process that much data at once. And then you can run several stages of getting rid of noise and getting rid of artifacts. And then at the very end, you can generate one of these beautiful Minecraft-like maps that all the algorithms can work with fairly well. But figuring out what the environment looks like and what you do with it is only the first step. The next step is how do you conserve energy and figure out where do you essentially need to go to be able to work in this environment, because you can't just simply figure out there's an object and drive up. You may not be able to use your robot in a certain way depending on how you position yourself, so that's a lot of work that we've looked at. Where is a robot actually really good at operating in the workspace? That's essentially where it's green. And where does a robot essentially have no ability to pick up things or even reach because of the mechanical limits? And what you get by doing so is you have the ability to react to change. So what's usually not possible in robotics is to, once you press start, to react to changes. So in this case, we could react to the object that was moved by the operator, and then also when the target gets moved, you can adapt to it and be more interactive with what the people do without requiring to stop. The second thing is, if you want to move away from cages, is how do you make sure that you're still safe when somebody does things they're not meant to do? And in this case, what we showed you earlier with this Minecraft-like environment representation, we can actually be able to detect when someone is moving into where the robot wants to move, stop the robot safely, and then just immediately resumes once it's clear. And all of that kind of can look like this. So in this case, again, you see as earlier on the right-hand side what the operator sees, and that's essentially what you will get when you're entirely separated in a different room in a different city. And then on the left-hand side, you can see what the robot does. And with the system, we can have things run automatically. So that's kind of like picking up a bottle. We can have things run semi-automatically. It's like the person saying, look, there's a box that's in my way. And the robot will then be able to figure out how to push it away. And then you can do a full control, like with a remote control, where you can literally drive it around with a joystick and execute and figure things out. But where is this useful? It's useful in a lot of areas where you don't want people to go. And that's because they would be in harm's way. So if we're talking about nuclear decommissioning or operating heavy machinery underground, it's fairly dangerous for people to be there, and we'd like to get them more in front of a computer to do remote control rather than having them to be in harm's way. And that's kind of like a summary. So we took this system to an international competition.
Our robot is a mobile manipulator for extreme environments. So we're trying to have a shared autonomy system that is very robust to changes and is able to go into dangerous environments and use the human operator as the high-level person who gives the instructions, with the system itself being able to complete missions semi or fully autonomously. So when trying to develop a platform that goes into the real world, we don't have all the luxury that we have in a robotics lab, such as knowing exactly where the robot is, how it's moving, how fast, to which position, when it's exactly turning, which makes controlling and especially identifying objects of interest, so the whole perception pipeline. What is something that we want to manipulate? What is an obstacle that we're trying to avoid? And what is something in the environment that can act like as a tool, like a lever to open a door? Really, really hard. But we're still trying to do that autonomously and build our perception systems without taking prior knowledge into account. I think the importance of the events is not only to being able to test in the field and like network with other researchers, and especially companies and stakeholders such as governments that work in this area. There is a lot of opportunity to integrate solutions together and basically eliminate a weakness that one system might have with the strength of another system.
So I'm actually fairly excited about what we saw here, because when I started in robotics like 10 years ago, that would not have been possible to do that easily. And I think that's some of the key takeaways, because now we're at this age where the robots are really coming, but they're not what you may get in media. They're not going to take all the jobs. They're not going to come after us. You've seen a lot of failures here. The second is, we're now having an open source community that is very vibrant, so you can actually pick up things online and there's a lot of help, and that's something that just has started about 5 years ago, and I think that's why it's really interesting to see how the next 5 years pan out. And then finally, as we saw in the beginning, we're finally at this age where you can make things truly move. And that's actually fairly exciting, and it's when something works, it's something that really gives you joy. And then finally, I've shown you some of the research progress that we've been doing over the past few years. And that's actually something that we're continuing. So a lot of that we think helps industry and helps us bring jobs back to Europe. So we're working on commercializing the system as of recently, and that's kind of our vision. So the idea is you have a factory that is traditional, but you completely put a lot of robots in, and without having to change the environment, you can have a single operator control the entire environment with the robots that we've been seeing, and we also think that's a good way to get a lot of the exciting events or the exciting research that we've been seeing in labs out into the real field. And finally, we are hiring, and that's at the Edinburgh Centre for Robotics, which is one of the European leading centres in all different kinds of robots. So we do submarine, we do the stuff that I've just showed you with humanoids, with mobile manipulation. Also, we do a lot of social interaction and how do human and human-robot interaction work. So we have postdoc and engineer positions opening immediately. We have PhD student positions for those of you who are finishing that are coming up, and we also have interns in for more of like a business or startup space starting next year. All right, thank you very much.